All right, we spent a lot of time doing electronic configurations and drawing orbital diagrams. And the outcome of that process was finding out that we had core electrons and valence electrons. And remember, the valence electrons are the ones in the highest S and P orbitals, so the highest energy level, those electrons that are in S and P orbitals at that highest energy level are valence electrons. And the valence electrons are important because they have to do with the reactivity of different elements. And when we talk about elements reacting or compounds reacting, we're talking about the forming and breaking of bonds. So let's look at what we're talking about when we talk about chemical bonds. So a chemical bond is just a force that holds one or more atoms together, right? And so these bonds come in different types, right? We have ionic bonds, and we have covalent bonds. And ionic bonds tend to be formed when we have a metal plus a non-metal. And the reason being is that metals tend to form cations or have positive charges, and the non-metals over here tend to form negative charges and form anions, and so then that positive charge on the cation is attracted to the negative charge on the anion, and then that electrostatic force holds those two ions together in what's called an ionic bond. And covalent bonds occur when electrons are shared instead of transferred from one thing to another. And what determines if you have an ionic bond versus a covalent bond, it can be predicted based on the electronegativity of the elements, actually the difference in electronegativity between the two elements participating. And electronegativity is somewhat of an arbitrary scale in that it really doesn't have units, but what you need to remember is the electronegativity increases in this direction as we go up the periodic table. So fluorine, which is up here, the highest level halogen, was assigned an electronegativity of 4 as the highest value, and then everything below it and to the left has a lower number. So the greater the difference in electronegativity between the two atoms forming a bond, the more likely one is to transfer the electrons to the other. So things on this side, these metals have low electronegativity, so they're not holding on to that electron very tightly. Non-metals over here tend to have high electronegativities, so they can actually pull that electron away from the metal, and then you end up with a positive charge and a negative charge. And when these metals and nonmetals form charges to make ionic bonds, we can predict what kind of metal, what kind of charge they're going to form by where they are on the periodic table. For example, if we look at sodium, which is a group 1A element, group 1A's form a +1 charge. But the reason for that is if you look at the electronic configuration of sodium, it looks like this, right? And so our highest energy level is energy level 3. We have 1 valence electron. So everybody in group 1 has 1 valence electron. If we moved over 1 element, we would add 1 more electron, and so we'd have 2 valence electrons, and we would form a +2 charge. And how this ends up working, if we look at a nonmetal like chlorine over there, right? Its electronic configuration is going to look like this. 3p5 is its ending point. Right, and then if we look at the valence electrons for chlorine, we have 7 valence electrons. So it needs 1 more valence electron to fill that outer shell. Sodium would need 7 more valence electrons, or it needs to lose 1 to have 8 in its outer shell. So then sodium tends to lose this valence electron, and then it becomes Na+. Chlorine ends up picking up that electron And then as Cl minus, it has 8 valence electrons. Now sodium with a +1 charge has 8 valence electrons. So they both think they have a full outer shell. And then if you have the sodium with a positive charge, it's going to be attracted to the chlorine with a negative charge, and you end up with with sodium chloride as the resulting compound.